Hi everyone, my name is Fulya and today I am here to present you our paper titled Improve the Acyclicity Reasoning for Bayesian Network Structural Learning with Constraint Programming. Bayesian networks are graphical models that represent probability distributions. We have a DAG where each vertex corresponds to a random variable and the edges denote direct conditional dependencies. We associate with each vertex a CPD so that the DAG together with the local CPDs gives a decomposed representation of the original probability distribution. Here, we are interested in learning a Bayesian network using discrete data. We take a set of observations as input and we try to construct the simplest BN that is most likely to generate that data. So it is a two-step process. First, we learn the structure of the BN, in other words, the underlying DAG. And second, we learn the conditional probabilities by using the dependency relations embedded in the structure. So for example, we learn the probability of each value of x3 given x1, x2, and x5. Learning the CPDs can be done in polynomial time, and it is known that the BN learned from applying these two steps in sequence is globally optimal. However, learning the structure, the DAG, is NP hard. And despite the computational difficulty, people are still interested in BN learning because it is quite useful in a wide range of domains, including gene regulatory networks, risk analysis, and image processing. One of the methods widely used for BNSL is called score and search. This method uses a pre-calculated set of scores to formulate the BNSL as an optimization problem. For each variable, there is a predefined set of candidate parent sets with their associated scores. With this information, it is possible to define a decomposable cost function. We then try to find a solution that minimizes this cost function and that returns a network that is acyclic. We already said that it is an NP-hard problem, and here with this small example we can better see that it is not easy to find the optimal graph. When we assign all variables to their zero-cost parent sets, we obtain a cyclic graph. Here you see we have several cycles in the resulting graph with a total cost of 0. Finding an acyclic graph is however not sufficient as we want to minimize the total cost as well. Here we have an acyclic solution with a total cost of 15. But then here you see that you can minimize the total cost to 10, and that gives you the optimal graph. There have been various methods developed for score-based BNSL, including dynamic programming, heuristic search, mixed integer linear programming, and constraint programming. Here we are mainly interested in the latter two. One of the two state-of-the-art solvers for BNSL is called Gopnilp, and it is based on mixed integer linear programming. It does branching cut using cluster cuts. Cluster constraints in a directed graph are defined for each subset of vertices, and they force at least one variable in this cluster to take a parent set that is completely outside the cluster. The number of these constraints is 2 to the power of the number of variables. That is way too many to be efficient, so Gopnilp finds and uses only those that are violated. It finds these cluster cuts by exactly solving an NP-hard subproblem created from the current optimal solution of the linear relaxation, and it repeats this until it can no longer find a violated cluster. The other solver is called CP/S, and it is based on constraint programming. It defines one CSP variable for each random variable, whose domain is the possible parent sets. These are the parent sets for which we received scores, and the domain sizes will reduce as we explore the search tree. The CP model benefits from symmetry and dominance relations to efficiently solve the problem. It also uses a pattern database to compute lower bounds. When it works pretty well, but sometimes Gopnilp computes much better lower bounds. The global acyclicity constraint is very tricky to formulate and impose in an efficient manner. Earlier, I mentioned that the number of constraints needed to ensure global acyclicity is due to the power of the number of variables, which is huge. And because of that, Van Beek and Hoffman, in their CP/S solver, implemented an acyclicity checker instead of explicitly imposing acyclicity. This acyclicity checker looks at the current domains of the parent set variables. in order to verify that one can construct at least one complete solution that is acyclic. And for that, they try to construct a complete order of variables. They start with the empty set, in which they try to add variables one by one. Here I can start with variable 1 since it has the empty set in its domain. Same for variable 2. Then I can add 0 because it can have 2 as its parent set, which has already been added in the set. It continues like this, and if we manage to add all variables in the set, it means that the acyclicity can be satisfied. The time complexity of this algorithm is O(n squared d), where n is the number of variables, which is 5 for this example, and d is the biggest domain size, which is 3. We implemented a solver that we call ELSA that is based on CP/S. We incorporated several algorithms in it in order to rapidly improve the lower bound and reduce the domain sizes of the parent set variables. ELSA is a good trade-off between the other two solvers, as it still uses the cluster reasoning embedded in Gopnilp, but instead of detecting all violated cluster cuts like Gopnilp does, which is NP-hard, it detects only a subset of them in polynomial time, and this subset of clusters provably increase the lower bound. We started by modifying the acyclicity checker in CP/S so that it considers only the values with zero cost. I will give an intuition using an example instead of diving in technical details. Here it would be a good idea to see these costs as marginal costs, the costs that we add to the lower bound when the variable takes the associated value. The purpose is to see if there can be an acyclic solution whose total cost is equal to the lower bound. If this is not the case, it means that we can increase the lower bound. In this example, if we run a acyclicity checker using zero cost values, we see that already in the beginning there is no variable that we can add in the ordering. It is because there is no variable with the empty set that has a zero cost. And here you see that the graph constructed using zero cost values contain quite a few cycles. We call it a cluster when we detect a set of variables where a cycle is inevitable. In other words, a cluster is a set of variables such that there is no variable of which all the parents are outside the cluster. In order to get rid of the cycles, we need to add further constraints that we call cluster cuts. We do this on a special type of clusters called violated clusters to make sure that the lower bound will increase. When we are given a violated cluster, we must force at least one variable to take a parent set whose intersection with the cluster is empty. Here variable 0 has one value in its domain anyway, but variable 1 could have the empty set as its parent. Variables 2 and 3 as well. For variable 4, there is no parent set that is outside the cluster. As a result, we have this new constraint. Either v1 or v2 or v3 must be assigned to the empty set. Once we have this new constraint, it is clear that we'll have to pay a cost of at least 5. So we can deduct this cost of 5 from the cost of these 3 values and add it to the lower bound. As a result, 6 will become 1, 10 will become 5, and 5 will become 0. And the lower bound will increase by 5. We can be a bit more clever and try to increase the lower bound even more. So instead of taking the violated cluster returned by the acyclicity checker as it is, we can first try to see if we can minimize it. I won't go into details, but know that it's possible to minimize the set 0, 1, 2, 3, 4 to the set 1 and 2. And if you look here, you'll see that that between variables 1 and 2, there's already a cycle, so it also makes sense. The cluster then becomes v1 equals the empty set or v2 equals the empty set. This way we get to increase the lower bound by 6 instead of 5. We did experiments with Gopnilp, CP/S, and our solver ELSA by using 54 medium-sized datasets with a 1-hour time limit and 15 large datasets with a 10-hour time limit. I will present the results for 17 of these instances. Here we compare ELSA and CP/S. There are 3 datasets for which CP/S performed clearly better, but for all the others, ELSA is faster. On top of that, there are 8 datasets for which CP/S does not even manage to find the optimal solution or prove optimality within the time limit. Here we compare Gopnilp and ELSA. There are 4 datasets for which Gopnilp performed better, but for all the others, again, ELSA is faster. And here there are 9 datasets for which Gopnilp does not manage to find the optimal solution or prove optimality within the time limit. With this work, we managed to exploit and improve on previous work on linear relaxations of the acyclicity constraint, and we explored a better trade-off on the axis of strength of inference versus speed. In the following, we will try to exploit the structure of the domains to better cope with large domains and further improve the performance. Thank you very much for your attention, and I will be glad to answer your questions if you have any. Take care.